All right, I will share my screen. Presentation mode. All right. Welcome everyone to our presentation on carbon in the built environment, and we'll talk both operational and embodied to take a holistic look at carbon in buildings. I am Patrick Murphy. I'm the Director of Sustainable Design at Vanderwall Engineers. My background is academically as an architectural engineer, so more of like a multidisciplinary approach to building design, building science, always interested and focused on energy and sustainability. I spent 10 years as a mechanical engineer and an MEP project manager. That's where I met Suzanne when she was working with Vanderwall in my current role. And then about 6 years ago, I came to the Boston office to lead our building performance group. That's our sustainability and our energy analysis team. Suzanne?
And I'm Suzanne Robinson. So my background is I started off as a structural engineer and then went to grad school for architecture, and then basically spent the last 15 to almost 20 years in the sustainability field, and was able to come back to my roots. So I'm now at Emitter, where I'm the Director of Sustainability, working on basically empowering the engineers to speak the language of sustainability on their projects.
So our agenda today, we'll go through an introduction to defining carbon and its role in the built environment. And then from there, Suzanne will do a deeper dive into embodied carbon. Then we'll take a minute for questions, and if you need to take a break, there'll be a couple minutes there. Then when we return, we'll come back to a deeper dive into operational carbon emissions that I'll be presenting from the MEP side. And again, another round of questions. And then Suzanne's gonna bring us home with kind of talking about the intersectionality and how operational and embodied carbon can work together sometimes, but can also compete with each other sometimes. And then we'll wrap up. So, to dive into the role of carbon in buildings, hopefully I am preaching to the choir on this, but the effects of global climate change and the rise in global temperatures is directly related to human-caused emissions, CO2 emissions, and the goal that the United Nations has established was ideally to keep it at 1.5 degrees Celsius or lower, and certainly no more than 2 degrees Celsius. So to get there, we need to decarbonize our entire economies. And we as a building industry, I think, had a little bit of a head start in the last several years thinking about the carbon emissions associated like with using fossil fuels in our buildings, but now we're starting to realize that to decarbonize the entire economy affects everything relating to the building industry. And we need to move quickly in order to hit these targets to limit the rise in global temperatures and prevent the most catastrophic impacts of climate change. And so really what that means, the faster that we can move as an industry, the greater the impact we're going to have. So the goal is to do as much as we can by 2030. And you're starting to see that make its way into codes and policies, certainly on the operational side, certainly with Massachusetts's new energy codes, for example, and some of the fossil fuel bans in a number of places. But then, we still have a ways to go beyond that, especially in the embodied carbon space. And we need to get to zero emissions by 2050. We've, I think, as an industry, already addressed a lot of the lowest hanging operational emissions and energy fruit, but now we're going through this electrification kind of transition, which helps certainly, but eventually there will be things that are just harder and harder to decarbonize. And so I think the rationale is that we need to move quickly to decarbonize what we can, what we know, what the technology that's already available is, because we know we're going to need a little bit more of an effort further out to decarbonize some of the harder things. Buildings globally are responsible for roughly 40% of total emissions. And of that, the majority is building operations. But when you think about it in the context of all of the existing buildings that are out there and operating, when a sizable portion of that is building construction, which only happens like a one moment in the life of a building. And when you look around a city, there may be a lot of construction going on, but proportionally compared to the carbon emissions associated with the city or with all the buildings in the city, construction has a disproportionately high carbon footprint. But in total, we're talking about 40% of global emissions that we as an industry have responsibility for. And the life cycle of a building is really like what we're now starting to widen our aperture from, not just focusing on operational and thinking about the big picture. And that goes all the way from the extraction of the materials that go into our buildings, through the manufacture, the transportation, the construction process, the life of the building, the operating of the building, all the way through the end of life, the demolition and the disposal. So, we as mechanical engineers, as energy analysts, are really focused on those, however many years that the building is being used and operated and maintained. But we do need to zoom out and to think about this entire spectrum. So focusing on first on the lifespan of the building, the operational carbon, it's cumulative. It adds up year over year. And so from the initial construction, you have, however many emissions you have each year, you basically add a similar amount year over year. At some point during the life of the building, there's a natural renewal cycle to upgrade or replace equipment that's at the end of its life, or you go through a larger renovation. And those, in theory, should be making the building more efficient. So you start to bend the curve of the cumulative emissions. So you're adding less emissions after each of these renewals. But when you think about it in the context of this is a cumulative amount of CO2 that we're putting into the atmosphere, it kind of it makes it clear that everything that we do now has a long-term impact. And those operational emissions are defined in three kind of buckets or scopes. The first are scope 1 emissions. Those are direct emissions. If you burn it, it creates an emission, goes into the atmosphere. So for example, if you have a gas water heater or a gas boiler to heat a building, that consumption of fossil fuel and the emissions that go out the stack are your scope 1 emissions. Scope 2 emissions are the indirect emissions associated with energy consumption in buildings. So that can be, for example, that you're purchasing electricity from the grid, and that electricity is generated by an array of sources, but that includes a coal plant or a natural gas power plant. And so those, the electricity generation has an emission that you are indirectly a part of through the consumption of that electricity. That also applies to campuses, especially like corporate and college campuses that have a central heating plant. The building itself might not have fossil fuel consumption, but it's consuming campus heating from a source that does have an emission. And then the last one is indirect emissions associated with operating buildings. And that's more of like how people commute to the office or to school. That's how like the supply chain of materials that come and go, to run the building are the ones that honestly we as designers have a limited ability to control. So this is all based on the premise that the grid is getting cleaner over time. This is a vast oversimplification, and we could have another hour and a half just on this topic, but we're seeing a transition away from the use of fossil fuels in the generation of electricity. That is also tied at the same time to we're seeing nuclear power plants coming offline. Even though nuclear is a carbon-free energy source, we are seeing a lot of production. If everyone could please mute their lines, and Suzanne, you might have the ability to do that with the host function. So the transition away from fossil fuels is supposed to be, in theory, met by the increase of renewable energy that is coming on from onshore, offshore wind and solar. And then simultaneously, we're reducing energy consumption through increasing the efficiency of buildings. But when we zoom out beyond just the operational emissions, then you have this total carbon life cycle of project. And so now we're going through an effort to measure that total carbon footprint. Thinking about the embodied carbon, so similar to how I had shown before, you go through a significant amount of carbon emissions associated with the construction of a building. So that's what we're seeing on the far left. That initial construction has a big carbon impact, and then you're basically steady state until you do those building renewals, updates to the buildings. So similar to how we see adjustments over time to the operational emissions, we do have some embodied emissions associated with updating buildings over their lifetime. When you add them together, now you start to get a sense of the total carbon emissions of the lifetime of the building. And it starts to make clear where we have the ability as designers to focus on reducing the carbon impact of projects. So I do want to give an acknowledgement. A lot of the slides that you just saw are from Goody Clancy Architects. They are a partner to both me and Suzanne. Their lead sustainability person, now Elaine Hoffman and Lori Ferris, have developed a lot of the thinking around this. And so Suzanne and I also present with Goody Clancy on this topic. So I want to give them credit for some of that content that you just saw. So here, I'll hand it over to Suzanne, who will walk us into a deeper dive on embodied carbon.
Wonderful, thanks. So I just put in the chat for those who joined a little bit late, just make sure everyone has the link to the continuing education credits. And I will, and so please fill out the Google form. Okay. So there we go. And everyone's seeing that, hopefully. Okay. So for the embodied carbon, I'll run through some basic overview information, specifically around embodied carbon, the impact of embodied carbon, how we measure embodied carbon, and then specifically doing a deeper dive in this section around embodied carbon and the structures, the work that the structural engineers do. So again, Patrick gave a good overview of how we're starting to look more globally at our carbon footprint and understanding it's not just the operational carbon of a building that provides an impact to global warming, but the whole lifestyle, the whole lifespan of the material and stuff. And so here you can see the amount of CO2 of tons per year that are being emitted globally. So when we look at total carbon emissions, we've got the embodied carbon, we've got the operational carbon, and then the transportation. So those are the three main factors that we're looking into, two of which we have a huge component with the buildings. When we talk embodied carbon, Patrick had touched on this, we have these life cycle stages that are broken out and have nomenclature. So you'll start hearing, if you haven't heard already, a lot of shorthands about these modules. So we have the extraction of raw materials, the transportation of those materials to the factory to then manufacture them. Those are your A1 to A3, and that's where you see a lot of the data currently around the impact values for embodied carbon. Then you move on into taking those materials and bringing them to the construction site. So if you're importing something from across the world versus sourcing something locally, that will have completely different carbon footprints, and then also considering the modes of transportation as well. anything being trucked is your highest impact for embodied carbon. So sometimes actually shipping something over from Europe will have less of a footprint, less of an impact than having something driven from, let's say, the West Coast over to the East Coast here. So it's really understanding those data points. Then we have the module B, which is really taking a look at the life of the materials in the building. And so this has to do with maintenance, repair. You'll see in here, there's also the operational carbon, B6 and B7, and then end of life. So what's happening to these materials, the carbon footprint regarding just demolition, hauling that material away, potentially recycling or dealing with disposal. And then there's this other kind of catch-all category, D, which is beyond the life cycle. And this has to do with potential reuse and recovery throughout that. So when we're looking at embodied carbon, the importance of embodied carbon is being recognized. This is from the Carbon Leadership Forum's website, some of their graphics. And they're showing that in our current state, embodied carbon is a decent sized piece of the total carbon pie of a building. But as we green the grid and have higher efficiency buildings, that is going to actually reduce, making the embodied carbon component of a building much larger. So that's why it's very important to focus on both. So if we're looking at, this is a report had shown basically the estimates on total carbon emissions for new construction over the next 30 years. And so there'll be a certain amount related to the construction, which is about 74%, and then the operational carbon aspect of that. Now, the importance of this is the time value of carbon. So as Patrick had mentioned earlier, we're really needing to keep things, our emissions below a certain level. Oh shoot, sorry. I just realized we have people in, I don't know how to do this. We have people in the waiting room, but Patrick,
I'll take care of it.
Okay, you can take care of it. Thanks. I didn't know if I had the only person there. So the time value of carbon, and I'll talk about this a little bit later in the last section, is understanding the total carbon of a building over this life cycle, but the time value is this first kind of 10 years is most important because we're really needing to reduce our carbon emissions. And so it's really giving more weight to the design decisions and operations in the next 10 years, basically.
Suzanne, actually, only you are the host. So if you make me a host, I can take care of.
Here, I figured out how to do it.
Okay.
I'll try to multitask here. Hopefully that will be the last batch there. So the last, so taking embodied carbon, taking a look at how does that break down within a building? And so these are really rough orders of magnitude understanding. We're still in early days of collecting data and understanding the embodied carbon of different elements and stuff. But structure is about 40 to 50% of the embodied carbon of a whole building process. Enclosures is the next. MEP definitely has a component, and then a lot of the interior finishes actually can have an impact too, but that kind of gives you understanding of order of magnitude. Oh, no, I can't get it. So let's take a look at measuring embodied carbon. So when we take a look at measuring embodied carbon, one thing I did want to throw in here is understanding kind of this new definition. We had an era there, we were working on net zero buildings. Now we're taking a look at net zero carbon. And so that's looking at the embodied carbon of a building, the operational carbon, and then any offsets. And the offsets can be both for the operational side, but also for the embodied side. So that has, your classic PVs, but then also you'll see here carbon sequestering. So I'll talk a little bit about that later, but the idea is being able to actually hold some of the carbon within the structure, within the building. So looking at how we approach projects, we really want to look at kind of 3 different buckets here. So we want to optimize the project. The best possible thing to do actually is building less, reusing more, cutting out that whole extraction of raw materials and manufacturing and transportation on the upfront side. And then optimizing your system is choosing low carbon systems. So for instance, in structures, we're seeing a lot more where we're looking at projects and we're looking, should we do a kind of traditional, conventional, concrete, steel structure versus mass timber or mass timber hybrid system, kind of looking at what are our system options. And then the last bucket is the optimizing the procurement. And so often a lot of people go to this first of like, let's do low carbon concrete and let's do low carbon materials, which is great. And we really want to be doing that, but we can have a lot of big impacts before we even get to specifying materials. So we have a look here at some terminology with LCA. So there's 2 types of life cycle assessment. What you'll see is material approach versus a building approach. So building approach, I'll start with first. This is basically taking a look at the life cycle analysis of all the building materials. If you're doing a whole building LCA, and you'll use different tools to do a calculation to understand your global warming potential of a project. And you might look at different scenarios and you can see different percentage reductions on your embodied carbon. On the material approach, we've had EPDs for a while. These are environmental product disclosures, and they are looking more specifically at material. They report some of that information that we were talking about with the different stages, specifically the A1 to A3 is usually what you'll see most often reported. And I'll dive into that a little bit more in a moment. So when we look at the stages of life cycle assessment, we have the material approach for EPDs is generally that A1 to A3. And then the building approach, LCA, is looking at more of a larger range of stages, usually A through C, the end of life. Now, when we look at the materials, this is from the Carbon Smart Materials Palette, which I believe is associated with AIA 2030. And they've identified kind of the top 6 high impact materials. And in there, you'll see some structural elements in there. So we have concrete, steel, and wood, insulation, which I'll get into a bit more on the enclosure side, and then carpet and gypsum. So let's jump into probably what's known as having the biggest impact is, oh wait, sorry, got ahead of myself. So looking at EPDs, this is an example. So what you'll see in the EPD document, they're third-party certified, so it's not just self-reporting. And in there, I'll have information around the embodied carbon. And so here's a little bit of a blow up where you'll see that sometimes there's industry average EPD information and then also product specific EPD information. So just understanding the nuance there. And then when we're calculating the LCA for a building, taking all the different materials, what we're doing is we're taking the quantity of a material and multiplying it by the impact value for that specific material. And that gives us the embodied carbon or some of the other impact categories. So it's much more straightforward, I will say, after having years of working in the energy modeling world of trying to do analysis on operational carbon and everything's interconnected. This is very independently and pretty straightforward to calculate from a mathematical point of view. However, it's understanding and getting correct and accurate information. So I did mention global warming potential. This is known as our embodied carbon. When we take a look at LCAs, we do understand there's a global impact. And so there's multiple factors that we want to consider. So climate change is a huge component of that, and that is related to our global warming potential. But there's other categories too that we want to be considering. So for instance, if you're doing a project that's going for LEED certification, LEED actually has you look at more than just global warming potential, more than just the embodied carbon. They want you to kind of to look at these other impact categories as well. So this can be anything from acidification, eutrophication in your water, smog formation, depletion of non-renewable energy, and ozone depletion. And so these have to do with, you know, mass timber is very popular right now because it has a lot of, it has a reduced embodied carbon footprint, but depending on the forestry practices, that actually can cause eutrophication, because you may be stripping the landscape when you're harvesting the wood in a non-sustainable way that could then impact with runoff and changing the chemistry of surrounding streams and rivers and such. So it's really understanding that whole impact. The other element here too is to consider the software. So there's a lot of software tools out there that look at various aspects of embodied carbon. They're still early days in development. And so there's not one main software tool that's kind of head of the pack, kind of like equivalent to Revit or something like that. I'll go over a few of these a little bit in my second portion of this. But I think it's useful to keep an eye and test out and look at all of these. Personally, we're using Tally, and then also exploring one-click as the two kind of more whole building LCA analysis tools. When we're looking at the LCA and looking at comparing, this is an example, I have these out of order, of, let's say we looked at a steel structural system and a timber structural system. This gives you a kind of idea around global warming potential, where the green, which is the timber, has a much lower embodied carbon than a structural steel system in this particular case. But if you look at the eutrophication and the ozone depletion, those are actually reversed. So they have a higher, mass timber has a higher impact in those fields. So again, it's kind of opening up and looking at a larger set of criteria. And then one last thing to take a look at is end of life assumptions. So there's another term called biogenic carbon, which I'll talk a little bit further about when I get into the timber section. And so it's understanding how accurate the software is. And so the software, it's not that, I shouldn't say accurate, it depends on what data they're using. So for instance, this is an example that ran one project with Tally and then another same project with Athena, and they were getting different numbers. So it's based on different assumptions. So when you're looking at the software, it's important to understand what the inputs are and what the assumptions are that comes with the software. Okay, so getting into structure, I need to hurry it up here. We don't really fully, at least I haven't, when I started off as a structural engineer, I never really thought about where the materials were coming and how extensive the energy was to extract, harvest, and then manufacture the structural materials that were coming to my project site. So if we look at concrete, concrete has the extraction of all the main materials. The largest component of embodied carbon is actually the cement manufacturing. And there's two components actually. So this one I thought was interesting. There's the energy related to the manufacturing process. We have to heat things up a lot to produce the Portland cement. But there's also a chemical reaction that's occurring too, that in that reaction releases more CO2 into the atmosphere. So there's a combination of things there. And then of course, coming through across to all the embodied carbon components to get the project, to get the concrete to the project site. Oops. Oh, there's arrows, sorry. So when we look at concrete, it's made up of aggregates, water, fine aggregates, sand, and then cement with some admixtures. So it's kind of our paste there, along with some air. And that piece of the pie, that Portland cement has the highest embodied carbon aspect. So if we look at it by weight of what's in your concrete mix, you know, in this example, coarse aggregate is, you know, by far is the largest component. But if you look at the impact of just the extraction of the materials, it's the Portland cement that by far outweighs the other impacts. Part of this has to do with the process for producing Portland cement. The key takeaway from this image is that number right in the middle, 1,450 degrees Celsius. So the energy to heat up the material to that level, to then be able to turn clinker into our Portland cement is astronomical. I had no idea until I started researching and getting into all of this. So what can we do? So Portland cement, we've been using that for decades, centuries. There are other options, and there's a lot of things we can do with the concrete mix. So one of the things you'll start seeing is this term supplemental cementitious materials, SCMs. And so it's looking at other options other than Portland cement, or reducing the amount of Portland cement and increasing some of these other options to still allow you to get that glue that you need for the concrete. So Portland limestone cement, which is this blended cement, type 1L, will be coming to the market in the near future. That's going to be reducing. We also have fly ash and slag that are already in the marketplace that we're using in our concrete mixes. Keep in mind that slag is a byproduct of the steel industry and fly ash is a byproduct of the coal industry. So it's a finite amount of materials. And as we close down the coal plants, we're actually reducing the amount of the fly ash that will be available in the marketplace. But we're seeing a lot of research and innovation around this. And so one product, for instance, is the ground glass pozzolans that we're exploring right now for some of our projects here in Boston. It's already being used in New York City, for instance, in DC and other areas in the region. So it's looking at taking our recycled glass bottles and such and grinding it up and using that as a supplemental material in the Portland cement mix. And so here's an example of some of the work that's being done, both in reducing the embodied carbon of materials, and then also looking at carbon capture. So carbon capture is how you can actually take some of the carbon out in the atmosphere and actually capture it and encase it within your concrete mix. And so that's another alternative of reducing your embodied carbon footprint. Okay, steel, real quick. Steel's, the two key things here is there's two different modes of manufacturing. There's the BOF, the basic oxygen furnace, and then there's the EAF, the electric arc furnace. The EAF uses a high percentage of recycled steel, and it doesn't have to bring the temperature up to such a high level. So they're able to really reduce the embodied carbon. So the more we can use recycled steel, the better. We do need the basic oxygen furnace because taking the iron ore, the raw materials to turn it into steel in the first place, you need those high temperatures. And until we kind of plateau in our steel demands, we're always going to need to be bringing more steel into the marketplace. So the more we can reduce the demand for steel, the better, because then the more we can be using the EAF based steel. We do have a bunch of domestic hot rolled steel mills in the area, and this is where a lot of our steel is coming from on projects. We also are seeing steel showing up in some of these Buy Clean programs. The California Buy Clean California Act basically puts GWP limits on different types of structural steel. So here's an example of some of that information. Okay, timber. With timber, the key takeaway from this image is there is embodied carbon that's being released throughout the process, but that big arrow pointing down is it has the potential to sequester a lot of carbon. So as we probably learned in elementary school or whatever, you know, with, oh, apparently I've forgotten the terminology. Anyways, leaves absorb the carbon and sequester a lot of the carbon in the atmosphere. When we cut down the trees, we lose some of that carbon, but a lot of it's still captured both within the trees and then within the root systems and stuff too. So then when we're building with mass timber, we're sequestering the CO2. Now, the key thing is understanding what the end of life is, because if you end up burning the timber, then you're releasing all that CO2 back into the atmosphere. So this is, with timber, very different from steel and concrete because it's more of a carbon cycle, where carbon is coming into the material. We're then able to take the material and construct with it and plant more trees to keep the cycle going, versus more of our fossil fuel systems with steel and concrete. You're just basically constantly just putting CO2 out there, unless you're coming up with some sort of sequestering new technology. So biogenic carbon is the term referred to the CO2 that is being stored within the material. So in this case, in the tree. And this can significantly offset the amount of embodied carbon that you're using to extract, harvest, manufacture, transport the materials. There are third-party certifications. There's FSC, and FSC has different levels, as we're probably all very familiar with. There's also SFI. The FSC is kind of known as the gold standard of forest management, of really maintaining, you know, going above and beyond kind of regulatory floors. SFI, it was created by the American Forest and Paper Association as kind of a competitor to FSC, an alternative. With mass timber engineered wood products, we have CLTs, we have glulam beams. Sometimes we'll see a full mass timber structure where the steel, the beams and the columns and the floor are all mass timber. Or you can have a hybrid where you still have, let's say, for instance, the structural steel beams and columns, and then you have the wood CLT deck for your wood flooring. So when we're looking at comparisons, here's an example of a project we were working on where we took the conventional steel framing and composite metal deck and then compared it to a hybrid option and then a mass timber option. And this is showing the reduction in embodied carbon for this project. Does not take into account the biogenic potential of actually absorbing some of the embodied carbon. When we take a look at this example and put it in relationship to the operational energy and the embodied carbon, we're specifically looking at the 10 years because those are the time value of carbon that we want to focus on. For this project, they were targeting a certain operational energy reduction. And so that was about 28% savings based on a high performance building, both on mechanical and envelope side of things. But then looking at the impact on embodied carbon by switching over to mass timber, you can see that has a huge impact as well too. And so it's something to consider as you're starting to go through and look at all your different options. And then I'm almost done here. So the carbon reduction potential, I feel like I've seen variations of the slide from day one of being in the sustainability field, is earlier on in the project, in the planning stages, is when you have the biggest impact and lowest cost of really whatever your sustainability goals are. So in this example, when we're looking at embodied carbon, build nothing, reuse existing structures. That's slam dunk easiest thing you can do to reduce embodied carbon. Build less, and so really look at how you can build with less, build clever. This has to do with how we can be more efficient with our materials, how we can reduce the amount of materials on a project. And then building efficiently has to do with really sourcing low carbon options and stuff as we go along. So the last thing I'm going to leave you with is a project example. This is not the project. I just found random pictures on the internet just to kind of keep the The project is still in design development, but it was kind of your classic project where you're seeing this gravity defying design work. And so it had a lot of cantilevers, a lot of elements that were pushed out. And it's recently had to go through some redesign, partly for budget reasons. And it basically brought everything in. It was more of a conventional style building without the cantilevers and stuff. And it was an interesting exercise because we do LCA analysis at periodic points throughout the project, just so we can understand the impact of some of the design decisions. And so we're not changing the material types or anything like that, but just the shift in the architectural design resulted in a 15% reduction in steel tonnage. And that was partly due to no more cantilevers, very minimal transfers, moment connections that we're needing that have a higher demand for the steel. So we're actually able to reduce by 15%, which is more than what we could have done by just sourcing lower carbon materials. So something to keep in mind. And then last thing I got to put a plug out there is just like architects have the AIA 2030 commitment, structural engineers, we have the 2050 committing to net zero for our structural components on our projects. And so there's a lot more information that is available on SE 2050's website. I did put some quick resources of some of the things I've talked about here that are useful for everyone. Okay, I finished.
All right, so during that, for those that joined a little bit later, I added to the chat a link. If you could please fill that out if you'd like continuing education credit, either if you're an AIA member, provide your number and the BSA will report that. And then if you're not an architect, don't have an AIA number, you can still request a certificate. So we'll take a beat if anyone has any questions about the content addressed so far before I take it away with operational carbon.
Patrick, it seems like there are 4 links in the chat. Are they all to the same thing, or are we trying to? Okay.
Yeah, it's just when somebody joins a Zoom, they don't see the previous chat. So it's as people were adding, we were just making sure that they got the link. All right, well, if there are no questions, I will keep going on the operational carbon side. So I'll go through the kind of context for operational carbon.
I have a question, if you don't mind.
Go ahead.
So on the embodied carbon, so that is a one-time carbon footprint, right? You produce the material, you get to the site, and you measure what the carbon footprint of that final product is, correct? And then do you take that number and carry it through the life of the building? So if it is 900, do you divide it by 30? So you spread it out equally for the length of the life of the building, or how do you use that number that, as I understand, maybe I'm missing something?
Yeah, no, that's a good
over
question.
at the moment that it's on site.
Yeah, no, and I think Patrick, you had a good slide in the introduction for this.
I'm pulling.
I could tell you're looking at this. So yeah, so Leonardi, the key thing is we want to understand what the carbon impact is for each of the years of the life of a building. And it's really important to look at the time value of carbon. So looking at the next 10 years. So for instance, we might say, oh, a certain type of insulation or a certain type of mechanical system will produce a lot lower carbon footprint over the lifespan of the building. But in this next 10 years, it only has that impact, right? Because you've divided it over that time period. Embodied carbon, you don't divide it over the lifespan of the, at least in the categories A1 through A3, which is kind of what we were talking about initially. And so that has a huge impact right at the beginning of a project. So the more you can actually reduce that the better your carbon picture looks in that first 10 years.
Yeah, one of the things, and what this chart is trying to illustrate is, we so often think about things in terms of an annual cycle. Like energy use intensity, for example, is based on annual energy use. When we zoom out and look at the life of the building, we're now thinking about cumulative total emissions. So you have a certain amount of emissions associated with the construction, and then year 1 of operational emissions, plus year 2 of operational emissions, and so on. And then you have the renovation of the building and the embodied carbon there. So you can look at it any number of ways, whatever is helpful to the question that you're trying to answer. But we're starting to see more of a focus on cumulative total lifetime carbon, because when you put it in the atmosphere, like it's up there. And so it takes a long time to basically get like reabsorbed into the oceans, or reabsorbed into, by trees and things like that, and put back, taken out of the atmosphere. So, I think it's cumulative total, and then think about like how long of a duration, that matters for whatever the question you're trying to solve is.
Yep, but you're still showing that initial on the graph. You can see that initial you actually showing as it is the same throughout.
Because it's cumulative. So that graph
Right,
was
exactly.
showing,
So you know highlighting that year 1.
You're already spent this much carbon. Exactly.
Okay.
Yeah, that is something I've honestly struggled with, some of the ways. I think as an industry, we've been trying to figure out how to communicate this concept. And I have struggled with some of the presentation of data around the idea of this first initial hit of carbon emissions is it's out there, like it's not happening every year, but like it happened, so therefore it is a part of your carbon footprint, and then you're adding to it from there with the operational. All right, any other questions before we move on? All right, seeing none, I will get back to the operational carbon section if I can. Nope. Hold, please. All right. So with operational carbon, we're going to go through some context around the different types of carbon, the approach to decarbonizing the operations of buildings, and dive more into electrification. Electrification and decarbonization kind of go hand in hand, and we'll show some components and strategies, what we do and don't mean when we talk about electrification and decarbonization, and then a couple of examples. So we talked about scope 1, 2, and 3 emissions. So scope 1 being if you burn it, it goes in the atmosphere. Scope 2, the indirect emissions associated with the consumption of electricity that's generated with fossil fuels elsewhere, for example. So we as design professionals have real control in a lot of ways over scope 1 and scope 2 emissions. And the way to get there is, 1, stop burning stuff to the extent that we can. And that's why you're seeing these fossil fuel bans in a number of states and cities. That's why you're seeing like the new energy code really start to incentivize electrification, moving away from fossil fuels. And then also take advantage of the grid getting cleaner over time, or force owners to add renewable energy to their projects, or through some of the laws like BERDO and the updated Cambridge Green New Deal, really incentivize owners to start purchasing clean electricity so that their indirect emissions are also reduced. And then realistically, that scope 3 emission, we as design professionals don't have much control over that, but that's something that's often handled with offsets. So we talked about that. So the goal is to not just electrify, it is also to reduce the loads on buildings and be more efficient. And that's represented by what I lovingly refer to as our wine bottle diagram. So what this is depicting is, on the left is the energy consumption with all the different energy end uses of a typical building. And so step one is reducing the loads. That's partnerships between architects and engineers to passively reduce loads, for example, with better performing envelope, solar shading, things like that. Then once you've reduced the loads and then you've incorporated energy recovery, now you're and efficient equipment, now you're electrifying that equipment. And so you're moving away from fossil fuels to ideally heat pumps, which also significantly consumes less energy than typical fossil fuel consumptions. That gets us down to the neck of the bottle. Once you've gotten that reduction in energy demand, then you offset with renewables, onsite or offsite. That's the cork of the bottle. So the philosophy is to really, not provide or require installing or creating a huge amount of renewables to support every new building. The goal is to reduce the demand from buildings so that it's more realistic for the amount of renewables that are coming online to be able to support those buildings. The ways that we get there, there's a whole array of strategies. I won't get into anyone specifically. You're probably familiar with a lot of them, and creative teams can implement these, all with the goal of reducing annual energy consumption. And once you've focused on that efficiency, now we start to pivot to electrification. So let me define what I mean by that. I'm going to compare three kind of very basic technology concepts and show you head to head what we do and don't mean. So the first is going to be a gas condensing boiler. That's the traditional, in the last, say, 15 years, approach to gas heating for hydraulic systems and buildings. Then we have heat pumps, and that's going to be an umbrella term, which I'll unpack a little bit later. And then the last is electric resistance. So you might be familiar with office buildings from the 80s that have electric resistance heating around the perimeter, or even sometimes houses have that in their baseboards. Think of the toaster oven, the glowing filament in a toaster oven. That's electric resistance. Starting comparing them by efficiency. So efficiency is basically however much energy you put in versus how much useful energy you get out. And so for the gas condensing boiler, you've got the energy of the fossil fuel going in. You get most of that energy out in the form of useful heat, 90+%, which is better than boilers in the past, which are more like 75 or 80% efficient. But you're still losing a decent amount of heat up through the stack. The heat, the hot air going up the stack is wasting some of that energy. Also, electric resistance, similarly, the electricity that comes in, it glows the filament, for example, and produces heat. And it's basically as much energy as you're putting in, that's what you're getting out in the form of useful heat. What makes a heat pump unique is that it has higher than 100% efficiency, which sounds counterintuitive, but the concept there is that you're inputting electricity into this heat pump, and it is taking that energy plus absorbing energy from somewhere else, from the air, from the ground, or from a water source, for example. It's absorbing more energy from other places and amplifying it. And that's how you get those higher percent efficiencies. A heat pump could have 200, 300, 500, 600% efficiency, depending on a bunch of different factors. For this analysis, we're going to use 300 as kind of an average. So right off the bat, and this is one example for one location, and we do this for a lot of different locations. The emissions for a heat pump to produce the same amount of heat is lower than for a boiler or for electric resistance. The numbers will change depending on the electricity grid or number of factors, but the general gist is right now you can produce the same amount of heat with lower carbon emissions than with a heat pump than any other technology. And the benefit of electrifying and by going with a heat pump is that it's not just year one, it's also, if you think about the lifetime, as the grid gets cleaner, it gives you opportunities for the future. The reason for this is not that the electricity grid is clean, the electricity that you're getting is not yet renewable, but it does have a mixture of sources. And in that current mixture of sources and the emissions associated with it, plus the efficiency of the heat pump, that's what gets you this lower emissions right off the bat. You see it illustrated with the electric resistance, the grid is not yet clean, so it is actually worse than the gas condensing boiler. But over time, as the grid gets cleaner or as an owner procures renewable electricity, we start to see that go down over time. And it could go down all the way to zero, depending on the location and depending on how much renewable energy is on the grid or is bought by the owner. Then the last thing is, let's compare cost, energy cost. Energy cost has been the metric that for the last, say, 20 years, a lot of the focus of energy analysis and investing in reducing energy in buildings has been focused on energy cost. Even LEED, the points for energy performance are based on energy cost savings, not necessarily emissions or energy savings. We're starting to see that change. But when we compare cost, depending on a number of factors, heat pumps can be competitive with the gas boiler. That's, again, electricity is expensive, just like, it's not great on its own, but when you couple electricity now with the efficiency of a heat pump, that's what makes these competitive. What you're not seeing, though, is necessarily any energy savings. It could be a little bit worse, a little bit better than the gas boiler. And so the paradigm that we've always thought about, or at least for the last 20 years, thought about energy conservation measures needing to pay for themselves, having a payback, doing a life cycle cost analysis, now maybe is not the right approach here. It's about how do we get to a zero carbon option the most cost effectively, and that's going to be a heat pump, but it's not necessarily going to pay for itself compared to the gas boiler, because gas is just frankly cheap. Components and strategies. So I've talked about heat pumps kind of as a generic term, but let me kind of dive into that a little bit more. A heat pump is basically using the refrigeration cycle that is moving heat back and forth through a refrigerant loop. And a heat pump is just like a window air conditioner or window shaker. If it's cooling the inside, it's basically absorbing heat from the inside and it's throwing it outside the building. The difference between an air conditioning unit and a heat pump is that the heat pump is reversible. It can go the other way. So in the winter, you can absorb, as counterintuitive as it seems, you can absorb heat from the outside and move it to the inside of the building to heat it up. And that's what makes a heat pump unique and different than air conditioning, and what gives it that higher efficiency. There are lots of different types of heat pumps. I won't get into the details of all these, but depending on the project size, the type of loads, the type of occupancy, there are different appropriate heat pumps for different applications. Air to water, air to air, water to water, lots of different combinations. I will acknowledge heat pumps are not a silver bullet, but they are probably like the most logical place to start. And they will probably get you, at least 80% of the way, maybe 90% of the way towards an all electric approach. And there are some liabilities, if it's an extremely cold day out in the winter, an air to water heat pump might struggle to produce enough heat on that extremely cold day. So you might need to supplement these. So one of the more common strategies that we're seeing in the last 2 years or so is an air source heat pump. You've probably seen before air-cooled chillers. This is basically the same thing, but again, a heat pump is reversible, so it can also produce heating. These are like, almost school bus size. They're outside. They're, I will admit, kind of ugly and kind of loud, but they are a strategy to produce both chilled water and hot water. And they can even do it simultaneously, because each one of these modules can kind of, depending on the model, can some be in cooling, some be in heating if you have simultaneous loads. Water-to-water heat pumps are, think like a ground source heat pump system, or for labs or healthcare projects, a heat recovery chiller or a heat shift chiller. What they're doing is if you have a chilled water loop and a hot water loop, and there's simultaneous heating and cooling going on, this device is shifting heat between those two water loops. So conceptually, a chilled water system is throwing the heat out through, say, a cooling tower. This device captures it before it goes to the cooling tower and puts that heat in the hot water loop to be used to heat the building, rather than firing a boiler to produce that heat. Ground source heat pump systems use the same concept as that water-to-water heat pump, but the thing that makes a large-scale geothermal system or ground source heat pump system work better than, say, an air source heat pump is the ground is warmer than the outside air in the middle of the winter. Similarly, the ground is a lot cooler than the outside air on a hot summer day. So that makes the heat pump more efficient, but geothermal systems tend to come at a pretty high cost because drilling the wells can be really expensive. And I'd be remiss not to acknowledge that there's lots of other loads in buildings that have historically been fossil fuel based that we are starting to electrify. And that includes the transition of the transportation sector onto electric. We're adding EV chargers that are now in the energy code, domestic hot water generation, cooking, for labs and healthcare, sterilization, for lots of different applications, laundry, humidification. All those are areas that there are strategies to electrify and get off of fossil fuels. So when you do all of that and apply them to some projects, this is kind of what it looks like. I'll start with one. We see these developer lab office buildings, popping up all over. How do you electrify these? That they're relatively difficult to fully electrify compared to other building types. So what we found was on this project, it took a while for the design to come together. The topic of electrification and decarbonization has really evolved over the life of this project. So the initial design was a good, efficient design and was reducing natural gas consumption by more than half compared to the baseline. But then we started to layer in some more of these technologies, like the heat recovery chiller and some more energy recovery. So a combination of, if you remember the wine bottle, more efficiency and also more electrification. And that got us to an 86% reduction in fossil fuel. What we're finding is for these relatively difficult, project types, high ventilation project types, you can get to 80, 90, even 95% reduction in fossil fuel consumption without breaking the bank, without making the system too complex. You start to see diminishing returns as you get to 100% for those more challenging types of projects, but we can see significant improvement. For the projects that do want to get to 100%, net zero. This is an example of a teaching lab that out on the Cape that just opened. And here we looked at those air to water heat pumps. So that blue school bus looking thing that I showed a few minutes ago. And it was located on the roof. We also made provisions to add renewable energy on the project itself. And what we found when we were trying to be all electric, no fossil fuel use was a resiliency issue. So I think the Cape, has nor'easters come by, the power is not completely reliable out there. And so the generator got larger to prevent a scenario like what we saw in Texas about 2 years ago, where they lost power for days in the middle of a cold snap, pipes froze, a lot of property damage. So for the truly all electric building, preventing that scenario, it caused a larger generator that was adding cost to the project. And so we looked at maybe let's, zoom out, and are we meeting our goal some other way without spending the money on the generator? So these are emissions over time. The lines are going down because the grid is in this analysis getting cleaner over time. The traditional fossil fuel approach has emissions annual emissions. So this is not cumulative. This is each year, the emissions over time. Our proposed 100% electric in blue was down here. So like a dramatic reduction in emissions. However, if we took a step back and said, you know what, in those emergency situations where it's extremely cold or we lose power, what if then we used a gas backup instead of the generator? And so that's what this hybrid option is in red. And so the lines are basically on top of one another. So, you know, what that told us was we can still meet the carbon goals for the project, but provide resiliency with different types of fuels. And then we offset with on-site renewables on the roof and then in the parking nearby. So again, remember that wine bottle we started with, you know, the base, we made the building more efficient, we then electrified, we made it, you know, the neck of the bottle, and then we offset with the cork, which was the on-site and off-site renewables. So our takeaways from this, you know, I keep kind of going back to this general concept, but we need to both do load reduction and thermal electrification. And hopefully you all, you know, are on the same page as me now about what we do and don't mean about electrification. And, you know, what we've learned from our projects is that electrification is a bit of a spectrum. On one end is basically business as usual, what we've been doing for the last 20 years, with no electrification at all, no plans for it in the future. At the other end of the spectrum is, you know, the shining example of full electrification with renewables and energy storage. Let's be realistic. A lot of our projects are going to fall somewhere on that spectrum. And I think it's our role as design professionals to try and push our projects as far, you know, to the right as possible. We are, I think, at a minimum, you know, and we're incentivized now with the building code to at least partially electrify, if not fully electrify projects. Adding renewables or enabling owners to either take advantage of the grid getting cleaner or you know, purchasing renewable energy themselves are, you know, strategies to really reduce or eliminate the operational carbon footprint of our projects. So with that, I will stop sharing, open it back up for questions before we kind of bring it home with kind of the intersection with Suzanne. All right.
I think, well, why don't we run into the last section here? Okay, let's see, that should work. Okay. So taking a look at the intersection of operation and embodied carbon, kind of giving you a quick overview on the two components of carbon. And in this, I'm going to focus a lot on the envelope because that really comes, both embodied carbon and operational carbon comes into some of the decision making for that. So again, reminder, you know, looking at all the CO2 emissions, huge, almost half of it is being emitted through the building industry, whether it's the construction or the operation of the buildings. I had shown this graph before where we were looking at structure, which was 40 to 50%, but enclosure is also a huge chunk there, 20 to 30%, both on embodied carbon, but then as we're seeing in the new stretch energy codes, really needed, you know, to reduce our loads to have a more high performance building, as Patrick was showing in the wine bottle diagram. So when I did want to bring this up, this was a report that had come out, I believe a year or so ago from RMI, Rocky Mountain Institute, and they had done analysis on low cost, high value opportunities to reduce embodied carbon in buildings. So there's concrete, rebar, but also insulation. So if you look at the carbon impacts of insulation, you have kind of your major categories here, and you can see how they are relative to order of magnitude of embodied carbon. The top yellow orangey-ish bars are showing the embodied carbon emissions, but then you're also seeing at the bottom here the blue bars, and what that's capturing is that concept of biogenic carbon, that carbon capture. So any kind of natural material is absorbing some of the carbon and is captured there. So depending on end of life and what you do with the material, it could potentially be a net positive on carbon reduction strategies. One of the tools that is useful to know is the kaleidoscope. And so this is specifically looking at embodied carbon for some of the key features that architects design. So envelopes, flooring, ceilings, partitions. This is was developed and is shared for free from Payette Architects, a local architect in Boston. So here's an example where you can see some kind of general order of magnitude understanding of different ceiling types. Within the tool, you can actually put in particular information, kind of compare different scenarios stuff. And so again, you're seeing the embodied carbon of kind of more conventional material use, and then some net positive embodied carbon, or I guess net negative, embodied carbon, where you're actually able to sequester some of those components. But if we look specifically at envelopes, you can see that depending on how you're structuring your envelope, whether you're having a masonry veneer, having curtain wall, rain screen, what have you, they'll have different impacts of embodied carbon. So you're wanting to take this information and then comparing it to the operational impact of your envelope components. So if you're looking specifically at insulation, you have different R values for, this is looking at per inch of material that you're putting in. So for instance, this table, this is from Building Green, looks at kind of generic categories. And you'll see here that the R value, so something that has a really high R value is basically our spray foam insulation that we've seen on a lot of passive houses and high efficiency structures. But then if you come over here and look at the embodied carbon, it has a fairly high embodied carbon relative to some other materials in here too. So now what we're starting to face as an industry is this question of, do I put in the higher operational carbon, but then now there's higher operational carbon, but now there's going to be this high embodied carbon impact overall? How is that going to impact things? What is the best choice, of kind of weighing things out for things? So I have an example here. So our enclosures group at Lemessurier was working on a project over at Northeastern University, Hertig Hall. So this was an existing building, or is an existing building. It's composed of the white brick facade, which is basically CMU block, bit of an air cavity, and then the brick. So very minimal R2 current existing conditions. The roof, kind of conventional TPO membrane, windows, single pane, par for the course for that era. And then also had some louvers in there, so Emitter louvers. So you can see proportionally surface area is what the pie chart is showing. So majority, of course, is the facade. The windows are a smaller percentage relative to the overall surface area. So looking at potential upgrades, we took a look at the existing R1 and proposed kind of a triple glazed R5 option. I think actually it was a double glazed, I think. And then same thing with the louvers, with roofing and interior insulation. Went through some analysis, did some energy modeling analysis on that for the different components. So this chart's basically showing if we just improve the roof, what's the impact? What if we just improve the windows? And then what if we just improve the interior masonry insulation? And then what if we combine some of those? And so what you're seeing here is that improving the masonry insulation has the largest impact, which makes sense considering it was the highest amount of surface area for that. We also took a look at the embodied carbon analysis. And so looking at what's the embodied carbon for the proposed improvements here. The spray foam insulation was relatively lower than some of the other stuff that we were looking at. And so what we were doing is having to pull all this information together and taking a look at the embodied carbon and the operational carbon saved. And what we did is we translated the operational energy reduction into operational carbon and put it all in the same units so that we could compare apples to apples here. And then what we did was calculate a carbon buyback period. And so this is the idea, kind of I loved how Patrick had mentioned earlier, we're still trying to figure out how's the best way to communicate some of these concepts. So we were playing around with, okay, what do we do with embodied carbon? What do we do with the operational carbon, so that we can merge them together and kind of understand how they relate to each other. So the carbon buyback period is basically looking at how long it's going to take that upfront operational carbon that happened at the beginning to be compensated by the operational savings carbon. And so based on that, we can see these different years, basically. And then we use the guiding principle of basically anything within the first 10 years, if you can buy it back, so you're actually still net positive in your carbon reductions within the first 10 years, then it's good to do that. The lower the number, the better, of course, because what that's showing is a lower embodied carbon relative to the operational savings that you can have for a project. So that's one example of combining operational and embodied carbon within the same analysis. The other thing that we're going to start seeing, we haven't seen yet, but I think with codes, with some of the new ordinances that are coming, both from the state level and from city levels around embodied carbon, is project teams are going to have to start understanding all the different design options, right? So whether you're doing heat pumps or other mechanical systems, bumping up your insulations, looking at the materials that you're sourcing. And so going back to the life cycle stages of carbon, what I think we're going to start seeing, and what we're looking forward to exploring in some upcoming projects, is actually pulling this upfront embodied carbon number and then also your operational energy carbon and putting those together in a master sheet. So instead of just the example that I showed before, where we were just looking at enclosures, we have all the different scenarios and we're able to bring it all down to a similar unit and understand what the best payback period is. And of course, you probably have to put in the cost in there as well, so you can understand what works with budget. Oops, sorry, I went too fast. So back to this, I did want to spend just in the last few minutes that we have here is talking about carbon reduction potential at each stage of construction, is specifically that first part, the build nothing. We're starting to see, at least I've been seeing from clients and portfolio owners, are really starting to take a pause and be like, wait a second, do we need to build new? Maybe we should renovate an existing building instead of demolishing it. And it's really interesting to see how that's actually picked up a lot. It's a lot more complicated renovating existing building. There's a lot more limitations and restrictions and stuff. And sometimes it can actually be more expensive depending on what you're facing. And there's another tool here called CARE tool. So this is the carbon avoided retrofit estimator. And what this does is it allows you to understand really early stage, big picture, order of magnitude impact of comparing renovating an existing building, leaving the building as is, or demolishing and building new. And so this is put together, I believe, through AIA 2030, but Goody Clancy played a large role in that. So definitely want to give them a nod here. So the taxonomy of the tool is basically you go through some easy interface questions, some questions around your existing building, some questions about if you're going to reuse the building, what you're kind of targeting, what you're going to potentially scope of work when it comes to your structure, envelope, interiors and stuff. And then if you were going to build new, what would you be considering when you're building new? You know, whether it was your conventional structural material or maybe mass timber. So here's some screenshots. What you can see here is the general information about the projects. You put in the location, zip code, you can put in your own grid information if you have that, or you can use default. It does pull from the EIA database of information. And then if you click through each of the tabs, here's just an example for the existing building where you're putting in some basic information around what the parameters were. So using this tool, I want to showcase a project that Patrick and I, Vanderbilt and Lemessurier, are both working on at Harvard University, 60 Oxford. This is a lab building. It's about 95,000 square feet, 4 floors above grade, and then a bunch of labs subterranean, 2 floors below. Architect is Payette, and the sustainability consultant on this is IES. So here what we have primarily it's research. So we have a lot of lab space in the basement, some labs on the upper floors, as well as meeting, conference rooms, offices, and general elements there. So we use the CARE tool to kind of understand and quantify some of the emissions around this project. So we're targeting a 50% reduction off of a typical baseline for the operational energy. And then for the embodied carbon, we aren't touching the envelope. There isn't any upgrading that's occurring currently, I believe, in this scenario that we're looking at. And so what you can see here is if we don't do anything, it has total metric ton CO2 up here. If we reuse and renovate the project, we have the substantially lower total carbon footprint. And then if we built a new building, it would be actually more efficient than the do nothing building if we were targeting the same operational carbon and some specific embodied carbon targets too. And so this helps you kind of understand, you know, it makes sense. We're renovating the building, upgrading the mechanical systems, really reducing the demand. So we're seeing a huge reduction on that operational emissions. And then on the embodied carbon emissions, we're not having to install a lot of new materials, at least on the structural side. So that's drastically structural and enclosure. So that's drastically reducing the embodied carbon. And so if you look at the graph here, what you're seeing is the do nothing, the green, over time is just going to have the highest carbon footprint. So after 25 years, it will be substantially higher. What's interesting to see is these inflection points. So at 5 years approximately is when the new building, although there would be some upfront embodied carbon, it would then become a better carbon scenario than if we had done nothing. So again, within this 10-year window, which is the most critical right now, it would still make sense to build a new building. But what's even better is if we renovate the building, it's always going to be better. There's no inflection points on that. Now, this is different on different scenarios, different cases, depending on your scope of work, what you're targeting for different elements. But it's an interesting tool, and I definitely recommend taking a look at it as you're kind of exploring different elements, because it does allow you to kind of put the operational and embodied carbon targets within a single analysis tool. Super easy to use. So I think on that note, I think we've finished in time here. I did have some resources here, links for the Kaleidoscope tool, the CARE tool. AIA had put together that toolkit, and then the Carbon Smart Materials palette. And on that note, I will open it up to any remaining questions.
The last call for anyone that's looking for continuing education. Hopefully by this point you've gotten access to that link. If you have not, let me know and I'll get you the link. Just make sure you fill it out before you go.
it is one of these things Patrick and I have talked about where this could definitely be a full course or a full study major. So lots of information to digest.
All right, well, maybe hearing no questions unless Leonardo, you got one.
Yeah, I got one. Just if you have any comments on educating clients, you know, for you as engineers, probably talking about devices and equipment, probably I can see many owners inclined to make the changes to the equipment, but going to do an entire envelope improvement, that's a different conversation. Thanks. So I'm wondering about your experience on that. And of course, you got all these tools. I guess you can make the case. But
I do find every project is basically like you do have to kind of customize your approach with each client based on what will make them be able to make a decision. So, for example, you know, I have an envelope study on a project that you know, realistically, like the windows are just like at the end of their life, they need to do something. So we went through a similar study to this, but through the lens of like, well, you got to do something. So what's the best approach? When we do like a larger analysis on a project, say an existing building, and we generally are finding it does not necessarily make sense to make the investment to improve the efficiency of something that you wouldn't otherwise be touching. You need to be touching that thing. Like you need to be replacing that piece of equipment or that window, or like you're already opening up the wall because you're doing some renovation. And those are the moments where the cost to incrementally make it better is not that bad. If you were trying to justify the entire project on like just replace the windows because they'd be more efficient, in all likelihood, it's not going to make sense from a cost perspective. So we find ourselves using other metrics than cost to help owners make decisions. So for example, you know, we could be using carbon, and like with the care tool example at the end that Suzanne had shown, you know, if say the windows are maybe they've got another 10 or 15 years of life in them, but you know, they're creating glare issues, or they're creating, you know, the solar load is pretty intense. And if you were to do something, or if in the winter, like it's, you know, you're getting condensation on the glass, or you're like, you find your like qualitative reasons, couple that with the kind of quantitative analysis, and that can help make the decision. But we find ourselves like on every job, like we've got to kind of figure out what the metrics are that will be convincing or make a decision.
Yeah, and I'll just add, I think Vern mentioned this in the comment section about incorporating into code. And so one of the things to keep in mind is not all places, it's mainly Boston, Cambridge, have these energy ordinances. So we're so used to the building code for new construction, major renovation. But now as we're doing new construction, we have to keep in mind these energy ordinances. So the building owners, if the building's over a certain size, incrementally over the next 30 years or less than 30 years, they're going to have to be below a certain emissions level. And if not, they're going to have to pay a penalty. So that brings the cost back into, hey, you might as well invest a little extra out front than having to pay out to the city, you know, down the road. So again, that's a relatively new concept. I know when I was on the owner side, trying to get our heads wrapped around that, because it's an operational budget versus the capital budget, and those have never been great at integrating, but you're starting to see that. And then we're also starting to see ordinances and codes looking at embodied carbon, because I will say the one thing, having worked in the energy world, it was always an upsell to be like, hey, pay a little bit more to have a higher efficient building. When it comes to structure and embodied carbon, less materials, less cost, and less embodied carbon, they're all directly, so there's usually other factors that are in play there too that you want to get to the bottom of. But good question.
Thank you.
Great. On that note, I think we've got everything covered. Thank you everyone for attending. We really appreciated it and look forward to future work incorporating these principles. So take care.
Thanks everyone.
Bye.